Now let's study fundamental identities, which is the first chapter of trigonometry. What is trigonometry? Trigonon is the Greek word for triangle and metron is for measure. So trigonometry is that branch of mathematics which deals with the measures of triangle in which one angle is 90 degrees. That is a right angle triangle. In trigonometry, there are infinite number of trigonometric identities which are nothing but equations with a left hand side and a right hand side with trigonometric ratios such as sine, cos, tan and so on. Furthermore, there are three basic trigonometric identities which are called the fundamental identities. But why? Why do we need these fundamental identities? The three fundamental identities are very important. Just these three fundamental identities of trigonometry allows us to prove infinite number of other trigonometric identities. Now, how can we solve these trigonometric identities? These trigonometric identities are basically equations. We simplify the left hand side and arrive at the right hand side. Now the prerequisites for this topic are, you need to know the trigonometric ratios of a right angle triangle. Now we take a right angle triangle in which angle B is 90 degrees. We can find the trigonometric ratios for angle A. Now how many trigonometric ratios are there? There are 6 trigonometric ratios which are sine, cos, tan, cosec, sec and cot. Now sine A is opposite side upon hypotenuse, cos A is adjacent side upon hypotenuse, tan A is opposite side upon adjacent side. Now cosec A is the reciprocal of sine A, sec A is the reciprocal of cos A and cot A is the reciprocal of tan A. Now there is a simpler way how you can remember the trigonometric ratios of sine, cos and tan. Can you remember Osha Chota? Here S, that is sine, is opposite upon hypotenuse, cos is adjacent upon hypotenuse and tan is opposite upon adjacent. I hope you remember these 6 trigonometric ratios. Now let's see which are the 3 fundamental identities. We take a right angle triangle, right angled at B. So the fundamental identities are sine square A plus cos square A is equal to 1. 1 plus tan square A is equal to sec square A and 1 plus cot square A is equal to cosec square A. I repeat, the 3 fundamental identities are sine square A plus cos square A is equal to 1, 1 plus tan square A is equal to sec square A, 1 plus cot square A is equal to cosec square A. Now let's prove these fundamental identities. The first one, we want to prove sine square A plus cos square A is equal to 1. We take a right angle triangle, right angled at B. So by Pythagoras theorem, we have BC square plus AB square is equal to AC square. Divide both the sides by AC square. Why are we doing this? Because we want to prove sine square plus cos square is 1. Now what is sine? The trigonometric ratio for sine is opposite upon hypotenuse. So we divide both the sides by AC square. We get BC square upon AC square plus AB square upon AC square is equal to AC square upon AC square. Now the first term we write as BC upon AC the whole square, second term as AB upon AC the whole square and the right side as AC upon AC the whole square. Now what is BC upon AC? It is sine A. So we have sine square A plus AB upon AC is cos A. We have cos square A, which is equal to AC upon AC is 1. So we have got the required result as sine square A plus cos square A is equal to 1. Now we want to prove the second identity, that is 1 plus tan square A is equal to sec square A. We take BC square plus AB square is equal to AC square. Now we divide both the sides by AB square. We get BC upon AB the whole square plus AB upon AB the whole square equal to AC upon AB the whole square. Now what is BC upon AB? That is opposite upon adjacent. So we have tan A square plus AB upon AB gives us 1 and AC upon AB, that is sec A. So we have sec square A. So the equation becomes tan square A plus 1 is equal to sec square A. Now we want to prove the third identity, which is 1 plus cot square A is equal to cosec square A. Now we divide both the sides by BC square. We get BC upon BC the whole square plus AB upon BC the whole square, which is equal to AC upon BC the whole square. We have 1 plus cot square A is equal to cosec square A. So now we have proved the three fundamental identities. Now we will prove some other trigonometric identities using these three fundamental identities. Prove the following identities. The first one, prove that tan 4 theta plus tan square theta is equal to sec 4 theta minus sec square theta. Here we start with LHS, which is tan 4 theta plus tan square theta. Now using this LHS, we want to arrive at RHS. Now in RHS, we have sec 4 theta and sec square theta. So what we need to do here is replace tans in terms of sec. Now first of all, from LHS, we can remove tan square common. We have tan square theta into tan square theta plus 1. Now what is tan square theta plus 1? It is sec square theta. So we have tan square theta into sec square theta. Now tan square theta we can replace as sec square theta minus 1. Using that same fundamental identity, 1 plus tan square theta is equal to sec square theta. Now we open up the brackets as sec 4 theta minus sec square theta, which is nothing but our RHS. So we have proved LHS and RHS equal. Now to the next problem, sine square theta upon 1 minus cot theta plus cos square theta upon 1 minus tan theta is equal to 1 plus sine theta into cos theta. Same way, we start with LHS. Now, in the denominator, we have cot theta and tan theta. We replace them in terms of sine and cos, because in the RHS we just have sines and cos. So we have sine square theta upon 1 minus cos theta upon sine theta plus cos square theta upon 1 minus sin theta upon cos theta. Now we take the LCM for the denominator parts. The first term becomes sin square theta upon sin theta minus cos theta upon sin theta, and the second term becomes cos square theta upon cos theta minus sin theta upon cos theta. Now, in the first term, sin theta is the denominator of the denominator. So, it goes to the numerator. So, we have sin cube theta upon sin theta minus cos theta. Similarly, in the second term, cos theta goes to the numerator. We have cos cube theta upon cos theta minus sin theta. Now, in the second term, you see, we have cos theta minus sin theta. We remove minus sign outside. We will have minus sin theta minus cos theta. So, we have sin cube theta upon sin theta minus cos theta minus cos cube theta upon sin theta minus cos theta. Now, the denominators of both the terms are the same. So, that becomes our LCM. So, sin cube theta minus cos cube theta upon sin theta minus cos theta. Now, we want to simplify this part. Sin cube theta minus cos cube theta. We know the formula in factorization for a cube minus b cube, which is a minus b into a square plus ab plus b square. We use that over here to get sin theta minus cos theta into sin square theta plus sin theta cos theta plus cos square theta upon sin theta minus cos theta. We have sin theta minus cos theta in the numerator and denominator cancels. So, we are left with sin square theta plus cos square theta plus sin theta cos theta. Now, what is sin square theta plus cos square theta? That is 1, the fundamental identity. So, we have 1 plus sin theta cos theta, which is nothing but our RHS. So, we have proved LHS and RHS equal. Now, let's solve the next problem. Prove that cos theta upon 1 plus sin theta is equal to 1 minus sin theta upon cos theta. We start with LHS, which is cos theta upon 1 plus sin theta. Now, if you look here, in the LHS we have cos and sin, and in RHS we have sin and cos. Can we do some replacement here? No, not possible. So, look at the denominator. We have 1 plus sin theta. In such cases, we rationalize the denominator, that is, multiply by its conjugate. The conjugate will be 1 minus sin theta. So, we multiply the numerator and denominator by 1 minus sin theta to get cos theta into 1 minus sin theta upon 1 plus sin theta into 1 minus sin theta. Now, the denominator can be simplified as 1 minus sin square theta, because it's of the type a plus b into a minus b is equal to a square minus b square. Now, the next step would become cos theta into 1 minus sin theta upon. Now, what is 1 minus sin square theta? It is nothing but cos square theta. using the identity sin square theta plus cos square theta is equal to 1. Now in the numerator and denominator we have cos theta, so cancel. We are left with 1 minus sin theta upon cos theta, which is nothing but our RHS. So we have proved LHS and RHS equal. Now to the next problem. Prove that 1 minus cos square theta upon 1 plus sin theta equals sin theta. Same way, start with LHS, which is 1 minus cos square theta upon 1 plus sin theta. Now again, here in the denominator we have 1 plus sin theta. So let's rationalize the denominator. We have 1 minus cos square theta into 1 minus sin theta upon 1 plus sin theta into 1 minus sin theta. Now that denominator part can be simplified as 1 minus sin square theta, which is nothing but cos square theta, using the identity sin square theta plus cos square theta is equal to 1. So we have 1 minus cos square theta into 1 minus sin theta upon cos square theta. Now cos square theta cancels. We have 1 minus 1. Now we open up the brackets. Before that we have a minus sign. So the sign within the brackets will change. We have 1 minus 1 plus sin theta. 1 and minus 1 cancel. We are left with sin theta, which is our RHS. So LHS equals RHS proved. Next problem, prove that 1 plus sin theta upon cos theta plus cos theta upon 1 plus sin theta equal to 2 sec theta. Here you see in the LHS we have sin and cos, whereas in RHS we have sec. What is sec? Sec is the reciprocal of cos. So in short, we want to write all the terms of LHS in terms of cos. Now if we look at LHS, in the second term we have the denominator as 1 plus sin theta. We can rationalize the denominator. But here you observe that in the numerator, in the first term we have 1 plus sin theta, which is same as the second term's denominator, and vice versa we have cos theta. So here the better option would be we take the LCM. You might be wondering, why not rationalize and do it? Why are we changing the method? In trigonometry, frankly, there is no method or rule which always works. It is always best you have to see according to the question what could be the shortest method. That will come through practice. So we take the LCM here as cos theta into 1 plus sin theta. The numerator becomes 1 plus sin theta the whole square plus cos square theta. Now expand the numerator. It is of the type a plus b the whole square. So we have a square plus 2ab plus b square. We write it as 1 plus 2 sin theta plus sin square theta plus cos square theta upon cos theta into 1 plus sin theta. Now in the numerator we have sin square theta plus cos square theta, that is 1. So 1 plus 2 sin theta plus 1 upon cos theta into 1 plus sin theta. Now add 1 and 1, we get 2 plus 2 sin theta upon denominator the same. Now from the numerator remove 2 outside, we have 2 into 1 plus sin theta upon denominator the same. Now in the numerator and denominator we have 1 plus sin theta which cancels. We are left with 2 upon cos theta. Now 2 upon cos theta gives us 2 sec theta, which is nothing but our RHS. So we have proved LHS and RHS equal.